Hello, my name is Jeff Michaels. I'm going to give you a short presentation on using Trammel points to lay out center lines, points, lines, arcs, and circles. And I'm going to show you the easy way to do it with no trigonometry. The presentation's about an hour long. It's broken into topics, so you can stop anytime you want and pick it up later. You don't have to watch the whole thing. But if you do watch the whole thing, you'll learn a whole basket of tricks that you can put together to really help yourself do layout work. I want to ask for you to share this information with others. I had people share it with me that I learned it, and so I'm just passing it on to you. And so if you run across somebody who would benefit from learning this, either you teach them or show them this video, and they'll get good too. I have a little backstory I'd like to share with you before I get really started. I worked in a fab shop in Cleveland, Ohio in the early 1970s. I worked with a bunch of displaced people from World War II, a lot of Eastern Europeans, and these guys were metal artisans. What they could do with metal was amazing. Using simple tools and simple methods, they could make it do whatever they wanted to because they knew how to do it. So I asked one old guy, where'd you learn this stuff? You know, I'd never seen it wrote down in any books or anything. And he said, well, how do you think they built the cathedrals in the 14th century? He said they had a measuring rule, a straight edge, a square, and a plumb bob, and a compass, which is a set of Trammel points, and the Pythagorean theorem. And that's how they built the cathedrals. So after you watch this presentation, you'll begin to see how these little simple tools, you can probably build a cathedral yourself, given enough time and experience. So with that, let's get started. So when would you use Trammel points? When you're doing metal fabrication work, sheet metal work, woodworking, flooring installations, arts and crafts, making sure the walls in your house are laid out square and true on the floor before erecting the walls. Layout scenarios where Trammel points are handy include drawing a circle, finding a point midway between 2 points, sometimes known as bisecting 2 points on a line, bisecting an angle, determining 90 and 45 degree angles, determining 30, 45, and 60 degree angles, duplicating an angle, a tangent of a circle, putting a perpendicular line to an existing line, putting a perpendicular line from an existing line through a point off the line, putting center lines on a non-square piece of material. This is something I did a lot. If you get sheet metal or sheet steel, it's usually cut on shears, so it has straight edges, but it's not quite square. It might be close, but it's not square. And so I did this almost every day as a steel fabricating layout man. This is the start of my work. And the next is putting a line on a perpendicular to a wavy edge and the end's not square, like a piece of hot rolled steel plate. I built about 6 miles of sewer outfall pipe that went into Lake Erie from steel that came right off the railroad cars from a steel mill. And they were like 15 feet wide and 60 feet long. And, you know, the edge is kind of wavy from how it's rolled, and then the ends are hit with big plate shears at the mill, so they're not square. So I had to learn how to put a line across the end that was pretty much perpendicular to this wavy edge. And then I could build center lines off that line and walk my way down the plate. So I'm going to show you that method too. I'm going to show you a method to make parallel lines. There's 2 ways to do it. Dividing the line into equal segments. There's 3 ways, 2 easy and 1 hard. Locating a point in XY coordinates off center lines. So once you got your center lines down, now you have to actually start laying out points or other center lines. And dividing a circumference into equal segments, also known as bolt circles. I'll show you the easy way and a harder brute force trial and error way to doing it. Accuracy and productivity. So let's talk fundamentals here before we get into techniques. When you're working to lay something out, remember to be accurate and efficient. Sometimes this means doing length measurements by trial and error rather than trying to determine the exact geometric answer. Now, while 100% correct takes too long to determine or has a degree of complexity that in itself may introduce errors just because it's so complicated. So KISS, keep it simple, stupid. If you're doing this for work, it's imperative to be accurate and efficient. After all, you're in the business of making money, not being academically correct. So you want to do the work accurately and as quickly as possible. Don't get stuck doing things right. Do the right thing. As you see, well, you'll see that. So some layout rules to live by. You might as well memorize these. Always double check your work. Periodically check your squares and straight edges for straightness. Measure it twice and cut it once. Try to measure it a different way a second time to check yourself in case the method you used the first time to lay it out is wrong. You had a method error. Use 3, 4, 5 triangles to double check every set of center lines before proceeding. This is fundamental because when you're doing layout work, you set your center lines and then you do the rest of the layout off those center lines. So if your center lines are wrong, everything else is wrong, and then you start all over or it's not accurate. So take the time, trust me on this, to just do your center lines and do a quick 3, 4, 5 triangle or throw a square on there just to make sure it's right. And then develop a plan to lay things out in a sequence to make sure you don't have to backtrack, which can lead to errors. So before you start, think of what you're going to do and all the layout work you have to do and where you're going to start and how you're going to progress through the whole job till you get to the end. If you do that, you plan your work and work your plan, it's a lot better than just kind of jumping in the middle and then finding out you had to do other things and it ends up getting inaccurate or waste a lot of time that way. Then plan the layout of material to be efficient and reduce waste. This saves time, money, and the planet. So here's an example. If you look at the upper left-hand picture there on this slide, this is the proper way to lay stuff out. It's all tightened together, and if you look, it's either at the top or the left-hand side, so you have this big piece of saved plate in the middle, or in the bottom right. On the top right-hand picture is the inefficient, improper way to do it, where it's kind of just dispersed all over the plate. So this one, you don't have steel plate left over for your next job. So not only that, it takes longer to lay out too, because if you look at that top left picture, you have the top and 4 sides across the top of the piece. So the top edge and the bottom edge of 5 of those pieces is one line. So you only have to draw that line once. Where on the right-hand picture, it's kind of spread all over. So you're going to be drawing lines multiple times. So you're being inefficient, and that's time. You're losing, you're taking extra time, so you're losing money. So plan your work and work your plan, I guess is what I'm saying. So now let's get into Trammel points themselves. Trammel points are merely a large adjustable compass or divider. And you use intersecting arcs and circles in conjunction with straight lines. You can create amazingly accurate layouts with no trigonometry. Trammel points are also a way to repeat a measurement many times, like to repeat a length. And like that old guy told me, that's how they built the cathedrals in the 14th century, when all they had was a measuring rule, a straight edge, a square, a plumb bob, and a compass, which is a set of Trammel points. And that Pythagorean theorem, a squared plus b squared equals c squared for right triangles, allows you to calculate some distances. So the Trammel points themselves are attached to a beam like a wooden stick or a rod or a pipe or a rule. Typical dimensions for wooden sticks are 1 inch by a ½ inch or 1.5 inches by 1 inch. Length varies depending on the need. 3 beam lengths usually cover every need you'll have. A 2-foot long one, a 4 or 5 foot long one, and an 8 or 10 foot long one should cover just about everything you'll need to do. Occasionally you need a long stick, but in this case, 98% of the time, these 3 will cover you. Trammel point tips. Trammel points have different points or tips. Sometimes these are called trammel heads. Sometimes it's the whole thing that goes on the stick. But one of them is usually a sharp point and the other is a marking point, which varies depending on the accuracy needed and the material the layout goes on. So typical points are metal scribes of various lengths, or a pencil or a round soapstone stick. When using only metal scribes, usually for a high accuracy metal work like machining, the surface is blued, and then the scribe marks the blued area with a very fine, accurate line. There are also specialty points or heads, including inside and outside calipers, as well as ball points. Ball points are used to draw a circle when it's necessary for the center point to fit in an existing hole, typically 1.5 inches or less. So here's some types of markers. You'll see some pictures of some Trammel points. These are Starrett 59A Trammel points. The top left-hand picture is a metal scribe center with the metal scribe marker. The bottom left-hand picture is a metal scribe center with a pencil in it. And the top right-hand picture is a metal scribe center with a soapstone stick. Down the bottom right's a little blurb about sharpening the soapstone with a file. If you file it at a slant with the inside edge being longer than the outside, like shown in that little picture there to the left. This way, one side of the line is the correct dimension instead of the middle of the line. So set your dimensions to the inside edge of that arc line, because this reduces error as the soapstone wears away. When you're making a big circle, as you start, it's going to run around and the soapstone's going to wear out a little bit and the line's going to get fatter as it goes around. Therefore, the middle of that line goes out a little farther as it goes around. But the one thing that doesn't change is the inside edge of that line. So it's a little layout trick. If you're using soapstone, you might want to remember. Ball points. So this is a picture of some ball points. You see where the center stick is. It's got that little half ball on it and then some balls underneath it. And those balls go in the hole at circle center of a hole that's already existing. And you use that to center the Trammel points. And then you use a metal scribe, a pencil, or a soapstone to make the circumference marks. It's amazingly stable and it works quite well. And if you find a need for them, they're handy to have. Using a 3, 4, 5 triangle. You use this to check your work. A 3, 4, 5 triangle is a right triangle, meaning one angle is 90 degrees. So you can use this as a check to make sure your perpendicular line is truly perpendicular. For really big work, you can use multiples of 3, 4, 5 to make as big a triangle as you can for accuracy. For instance, instead of 3, 4, 5, you can use 6, 8, 10, or 9, 12, 15. So what you do is you make your lines for the perpendicular line and then measure your 3 and 4 foot lengths on the perpendiculars and then measure the hypotenuse, the long side. In this case for 3, 4, you want that long side to be 5. If it's not 5, you either have to go back and adjust the perpendicular legs 3 and 4 or the angle in between isn't 90 degrees. So it's a real good check. Do it on center lines all the time. So note, we're going to get into the presentation now. So on the following slide, there's circles with dark arcs superimposed on them. These dark arcs represent what you're really going to draw with the Trammel points. The entire circle is shown to illustrate the geometry behind what makes it work. So in real life, you're just going to make the dark arcs, but it's really intersections of circles. So you'll see as we go along here. So before we get started, let's talk some fundamentals of circles. There's some general rules of thumb to keep in mind about circles and angles. 2 points on a circle define an interior angle. So if you go here to this top where the circle and this point is, that's on the circle. Down here at the bottom, it's on the circle, and that straight line in between is known as the chord. And the angle between those 2 points in the center of the circle that goes around those 2 points is angle theta. So drawing a line to divide the interior of the angle in half results in 2 right triangles. You'll see one here, A, B, and C, and there's another mirror on the bottom, A, a B, and a C. And that interior angle here is half of the original angle. And the long side, the hypotenuse of that triangle, is equal to the radius of the circle. So these are important things to keep in mind. It's going to be used to determine how to lay out points and either have them on center lines or straddling center lines. It also allows you to use that Pythagorean theorem of a squared plus b squared equals c squared on the right triangle and all the associated geometry techniques of right triangles. When you have two circles, two centers are always on the same line. So on the bottom left-hand little diagram, you'll see three circles, and any two you can put a straight line through, as I've shown here. On the bottom right-hand circle, showing no matter what the radius, whenever two circles of equal radius intersect, a straight line drawn between the intersecting arcs is always half the difference between the two centers. This is fundamental for using Trammel points, so let's look here a little bit. You have these 2 points separated by this distance L. So little circle R centered at the 2 points. And these are the arcs you draw here in dark. You draw a line through that, it's at L over 2. It's half the distance. If you draw bigger circles, big radius R, and draw these arcs, you'll see if you draw that line through it, it also goes through L over 2. So what this really means when you use Trammel points and you're using intersecting arcs is you don't have to measure that distance between your arcs. You're just using intersecting arcs to determine the middle, and it's always going to be the same. So you can just set your Trammel points. It's quick and easy and takes 5 seconds. You can draw a circle through 3 points too. You can't with 4, but you can with 3. So given the points 1, 2, and 3 below, draw a line between points 1 and 2, 1 and 3, and 2 and 3. Find the midpoint of each line, and if you use that technique I showed on the 2 circles intersecting on the previous slide, you can find those midpoints. Then you draw perpendiculars through those midpoints. I'll show you how to do that later, and they'll all center on this point C. That's the center of a circle that'll go through all the points. So if you draw that circle at C, the radius from C to 1, and C to 3, and C to 2 is all equal. So that's how you put a circle around 3 points. To find a point in the middle of 2 points, we're bisecting 2 points on a line. I'm going to just show you the quick and easy way to do it, not the theoretical way. So you have points A and B. You draw a line between them. You draw 2 circles of a radius with more than half the distance between the 2 points, so they're going to overlap, and you draw these dark arcs as shown here. You draw a line through those 2 arcs in the middle. That's point M, and that's halfway between the 2, and it's also perpendicular to the line AB. So this is how you find the middle and draw perpendicular at the same time. Determining angles. You can use Trammel points to lay out angles on a line too. You do this by drawing multiple circles and using the intersection points to determine angles. So, did you know the radius of a circle will fit around the circumference of a circle exactly 6 times? That's when that radius of a circle, being a straight line, goes from point to point on that circle. That means each interior angle is 60 degrees. So that makes it easy to determine 60 and 30-degree angles. This is how you build a hexagon. So I'll show you here. We're going to build a hexagon. So you have a straight line between 2 points on a circle is equal to the radius of the circle. The circle can be divided into 6 equal segments of 60 degrees each. So start on the left here, draw a circle. There's the point where it crosses. And we're going to do this on the horizontal center line first, so that's why it's in red. So I draw my first circle with an arc gone through the circle, second arc, third arc, fourth arc, fifth arc, sixth arc. If it's set properly, it'll go through the original point. I connect those points, and I have a hexagon. And you'll notice, because I started on the horizontal line, the top and bottom are flat, and the points are on the sides. If we go to the right diagram here, we're with the first circle on the vertical center line. That's the red one here, and draw the arc, and then step around the circle drawing arcs. Again, make sure that last arc goes through the original point so that the distance for those chords is correct. Draw the lines, and there's another hexagon, except this time the point's on the top and the flats are on the side. So It depends how you want to orient it as to where you start on the circle. Now we're going to talk about bisecting an angle. Bisecting an angle is used quite often. It's simple and quick simply by drawing 3 circles of the same radius, so it's really fast. So given an angle of unknown degrees with the center being point A, as shown there on the left in that little figure, draw a circle around point A. And you can just set the radius. You don't have to measure it. Just open it up, set it. So mark the upper point B where it intersects the angle and lower point C where it intersects the angle. Then draw 2 more circles, same diameter, same radius, around point B and point C, and where those points cross in the middle to the upper right, up here, label that point D. Then draw a line through point A through point D, and you have bisected that angle where this little bit of an angle right here is the same as this little bit of an angle right here. And that's it. Fast, easy, no measurements at all. So building 90 and 45 degree angles, it's pretty easy too. So given this line here on the bottom, mark point A on the straight line where you want to determine the angle. Draw a circle, mark the arc so where it intersects the line is point B, as shown there. Draw 2 bigger circles, because now it has to be bigger than the midpoint between A and B. And where they intersect here, you're going to draw a vertical line through it, call that point C, and you've bisected the angle. You've created a 90 degree with the horizontal degree. It's a horizontal line. For 45 degrees, first you start building the 90 like you just did. Then you draw 4 circles around point B and C, and you mark those intersections point D right here. You draw a line from point A through point D, or from point D to point D through A, and you have your 45 degree lines. For 22.5 degrees, you draw circles at C, D, and B, and where those intersections cross here and here and here, you draw a line through them, and just like you did above, you'll get the idea. To build 30, 45, and 60 degree angles, if you want 30 degrees from vertical or 60 degrees from horizontal, start on the horizontal center line. If you want 30 degrees from horizontal or 60 degrees from vertical, start on the vertical center line. So I'll show you here. Start with a set of center lines and the intersections point 1. So you draw a circle 1 around point 1, and where it crosses the center lines, you put the dark arc on there. You mark those point 2 and point 3. You draw a circle 2 around point 2, and where the radius to circle 2 crosses circle 1, you cross that, and you mark that point A. Draw a line from the center of point 1 through point A, and you get line A at 30 degrees from horizontal. To draw a 60 degree one, you center a third circle, same diameter or radius, or point 3. And then you draw the circle and then the arcs where it crosses circle 1 and circle 2. Where the arc for circle 3 crosses the arc of circle 1, that's point C. Draw a line through it and you get a 60 degree angle. Where the arc crosses from circle 2 and circle 3, you mark that point B and you get a 45 degree angle. So with 3 circles, you just determine 30, 45, and 60 degrees. And again, you didn't have to do any measuring. You just opened them up and laid them out. Duplicating an angle. This is something you have to do sometimes. So given this set up here at the top with point A and line K coming off of it, capital K, point A and line M coming off of it, there's an angle between those 2 lines. So down here, given line little m and a point A, we want to draw the same angle off this bottom line that we have on the top line. So it's really pretty easy. First, you draw a circle around point A, and where it intersects the 2 lines K and M in the upper drawing, you mark those points C and B. And you go down to the lower line and you draw that same radius, and where it intersects the line M, little m, you mark that little b, and you put an arc above it about where the intersection of the new line is going to be. Now you go back to the upper one, and on point B, you draw a little circle with a radius from C to B, and you come down to the lower line and you put it on point little b, and you draw the circle with an arc where it intersected the arc from little a. You call that point C. You draw a line through it, and there you go. It's the same angle as the line up above. And that also works if this bottom horizontal line here might be at 37.5 degrees. Well, you can still mark out that same angle because the geometry is irrespective of like positive orientation of that bottom line. Sometimes you have to determine the tangent of a circle, so here we'll do that. So given a circle with a center M and a point P outside that circle here, we want to construct a line through P to the circle radius here that's tangent to the circle. So it's 90 degrees for a line from the center to the edge, 90 degrees over here to point P. We'll do that on both sides. It's pretty easy, actually. First, you draw a line through point M and point P. You draw two overlapping circles, one around point M and one about point P, and draw the arcs in the middle. Draw a line through it, and where it crosses the original line, call that point N. And those are center lines, except now they're just tilted a little bit, but they're perpendicular. Now you go to point N and you draw another circle with radius N to M, and you spin the radius around where it intersects the original circle here. You mark those point Q. You draw a line from point Q to point P, and it's tangent to the circle M at this point. Same here on the bottom because it's symmetric. That's it. So putting a perpendicular line off an existing line is quite easy. You've seen it a little bit already. But given this horizontal line on the bottom, we want to throw a perpendicular line above it. So first, mark point C of where you want the line to intersect the existing line. Draw a circle, and where the arcs cross the horizontal line, mark those A1. Then draw two bigger circles centered on A1. This is a larger radius than the distance A1 to C. And where those intersect, draw your arcs. Draw a line through to point D, and there you go. You have a perpendicular line off an existing line. And again, you didn't have to measure any radiuses or anything. You just drew a circle, opened the points up some more, drew two more circles, you're done. So if you want to put a line perpendicular to an existing line from a point M off the line, it's also kind of easy, but I'll show you here the little trick. So first you draw a circle around point M, and at the bottom here you draw your arc where it crosses the horizontal line, two places. And then you mark those two places, and you draw two circles of a bigger diameter than the halfway point, and you mark the arcs top and bottom to build a perpendicular line. And lo and behold, it goes through point M. Pretty amazing how this first little half circle down here at the bottom that intersects the line twice is the secret on that. So putting center lines on a non-square piece of material. This is something I did every day. I'd get plate coming from shears or, from the warehouse, and it wouldn't be square, so I had to put center lines on it. So this is how you do it. You draw a long horizontal line on the bottom, about an inch away from the edge, and at the top you draw a horizontal line about exactly the same distance from the edge, but about in the middle. Then you measure the bottom width, and then you find the center and you call that mark C. So we're basically just going to throw a perpendicular line off it like we just saw. Mark your arcs A1. Bigger circles where those arcs intersect. Draw a line through it, and that's your vertical center line. Except you want to take it all the way to the other side to where it intersects that line that's 1 inch off the top edge that you drew there, point T. Because then what you're going to do, the point T is 1 inch, point C is 1 inch, so now you want to find the middle edge. So you draw 2 circles, one centered around point T, one centered around point C, and where the arcs intersect on the sides, you draw those. Put your line through it, and those are your horizontal center lines, and that's also half the distance of the height. It's really quite easy. It's like 3 circles, and you're done. 3 radius circles a few times, and you're done. So putting a line perpendicular to a wavy edge and the end's not square, like hot rolled steel plate or skill soft cut plywood, where your hand waves a little bit as you're cutting it. So a little backstory on this, I laid out 6 miles of sewer outfall pipe that go into Lake Erie. And it came in big sheets and railroad cars, about 15 feet wide and about 60 feet long. And the long edge was kind of wavy, like I show here. And it wasn't gross wavy, but it was, maybe plus or minus 1/4 of an inch. So what I had to do was throw a line off the end of it here that was perpendicular roughly to that wavy edge. Because then off that perpendicular line, I could build a center line and then start laying stuff down the length of the plate. If I got too close to the edge again, I'd just do that again and find a perpendicular line, a center line, and keep working. So this is how you do that. This is an old Polish guy taught me this trick. So you draw a line, L1 I call it, about 1 inch away from the bottom edge of the plate. It's parallel to the bottom edge, and it's going to be wavy too. I just set a machine to square about 1 inch, it doesn't even have to be exact, just, push it out, tighten the nut, put your chalk on it, and zoom, there you go. All right. Then you have to pick a point towards the end where if you draw a perpendicular line across, it's going to go all the way across the plate, depending on how the edge cut. So you'll just eyeball that. So you'll get a place the line will go all the way across. Then you draw 3 circles, and you mark this upper right-hand quadrant and where it intersects line L1. You move it to where it intersected L1. You draw another circle around, except this time you go to the upper left quadrant and cross the line you just drew in the first circle. You draw another arc of where you're going to cross it in the next circle, and you draw it where it crosses line L1 again. Then you move the circle to A3, third point, draw another circle and arc where you drew the arc for the second one. Okay, then you go to those intersections, I'm going to call them B1 and B2, and you draw 2 more circles, same radius, so you're not changing the dimensions of your stakes. And you draw one in the upper left-hand quadrant of that circle, the upper right-hand quadrant of that circle. You move over to B2 and you draw another circle, and you draw an arc where the circle you just drew around B1. Then you go to C1, I call that, and you draw another circle, same radius, diameter as all the other ones. And where it intersects the circle from B1, you draw an arc. You draw your line there, L2. You call that point D, and there you have a line that's perpendicular roughly to this wavy edge. And what's really cool about this method is that you'll see that point A3 is down a little bit, so point B2 is going to be down a little bit. Because B2 and B1 go together to make C1, it's going to be down about half as much, right? Even less because of the geometry. And then you're going to step it out over here to get point D. So it's really quite amazing. It kind of averages out some of the error you get on the bottom. If it's a ½ inch or quarter, an inch, that's too much. But plus or minus wavy 1/4 of an inch, you can do this. Then build a perpendicular off your line this way and start building down the plate. And if it gets too close to the edges, you just put another perpendicular on it and keep on going. If this bottom line is truly straight, then of course the vertical is going to be truly perpendicular and you don't have to worry about it. The good thing too about this method, this point D, is actually quite a bit away from A1. So you can see with these circles, if you draw these 4-foot circles, you're pushing this up 7 feet on the plate. So that gives you some pretty good angle geometry to ensure that line's really perpendicular versus doing it down here, you know. So marking parallel lines, this is something you'll do too periodically. So there's a couple ways to do it. One way is giving this horizontal line. You're just going to throw 2 perpendiculars at it off at 2 different points. So draw your circles, draw your other circles again with arcs. Throw your perpendiculars through it. You measure the distance you want to do it, and then you start at point 1, you draw an arc. You move the center up to where you drew the arc, and you draw arc 2. Then you move the center up to that, and you draw arc 3, and then you go over to the other perpendicular and do the same thing. And boom, you got 4 lines. Pretty quick. The only measurement you had to make was this distance right here. Other than that, it was just all opening the points, making sweeps, drawing a straight line with only 1 measurement. So the next method we're going to talk about to make parallel lines, I call method 2. It involves building a parallelogram using 2-dimension measurements. So given this line L here, and a point P off that line, say we want to draw a line through P that's parallel to L. So what we do is first we try and draw a perpendicular between P and line L. So we draw a circle, and where it intersects line L at the bottom there, you'll see the arc. You mark the 2 intersections, point A and point B. Then you go to point B and you set the Trammel point distance from B to P, because we're going to build a parallelogram. So you notice how A and B is to the right of A, so we're going to build a point to the right of P somewhere to kind of mimic A on the parallelogram. So we draw this segment in the upper right hand arc of the circle. Then we go to point A and we open our Trammel points up to the distance from A to B. Okay, and then we move that to point P, and where that circle arc crosses the arc we drew from point B, we call that point Q. Draw a line from P through Q, and that's line M, and you'll see it's parallel to the original line. So with 3 radius changes and a couple of sweeps on the Trammel points, we got our parallel line. There was no measuring involved because point P was already there. And so it's just as fast, it's easy. You just set the points, do some sweeps, set some points, do some sweeps. Sometimes you have to set the points, to the measurements on the plate, but it's fast and easy. So we're going to divide a line into equal segments next. There's a hard way and 2 easy ways. The hard way, while theoretically more accurate, is actually more complicated, and if it's complicated enough, it can cause unintentional errors. So I'll show you the easy way first, and then the hard way. So the easy way, this is where when a line gets divided into a number of equal lengths like a ruler. So you want to divide it in half, a quarter, an eighth, a 16th, a 32nd, a 64. So given this line from A to B, that's this length L apart, we're basically going to bisect it. So draw 2 overlapping circles, draw a line through those overlapping arcs where they cross the line AB, that's point C. And you'll notice that's halfway between A and B. So A to C is half of the line from A to B, and C to B is half the distance from A to B. Then what you can do is draw 3 more circles centered around A, centered around C, and centered around B, so you can divide those halves into quarters. So you see these dark arcs where they overlap, you draw a line through them. You do it on the other side here too. And then so starting left to right, you got L and a quarter. L and a quarter is equal to half. L and a quarter, and that's the whole. So again, with no measurements, I've just divided it into 4 different sections, and you can keep going and going and going. Realistically, there's a limit where you get to about 8 or 16 divisions, and you might be better off doing it the way I'm going to show you next. So now we're going to talk about dividing a line into equal segments, the easy way, number 2. So for an uneven number of segments, or not part of the previous method, break down and do the following brute force way using a ruler or tape measure. It's also good if the segment's not a whole number L or has confusing units like 3 foot 7.5 inches, So measure the length L divided by the number of segments and set the Trammel points to this distance. You need a ruler or tape measure for this method. If it's, a whole number or you good on your first guess, you'll get it right the first time, but you'll see what you do if you don't get it right, how you fix it. So what you do is you're starting at A, you make your sweeps, and you go all the way across to point B. And if you figured out the distance right, the last arc of the 5th circle should go through the middle of point B. So if it's a little short, that means the lengths aren't long enough. So what you do is you take this last distance between your last arc and point B, divide that by the number of circles you drew, in this case 5, and then you add that to your Trammel point setting, so your next circles will be a little farther out, a little farther out, a little farther out, a little farther out, and hopefully land on point B. If they go past point B, then you have to subtract some, so you measure the distance between the last point and the last arc and point B, divide that, in this case, by 5, the number of segments, subtract that from your Trammel points, and then you'll pull them back a little bit, and it'll add up as you go across, and hopefully your last arc will cross point B. Which is what I just described here. Pretty quick, pretty easy, no monkeying around. That way you're guaranteed the distance right. One thing you can do to double check yourself is to go backwards from point B and do your sweeps this way. And if you find that they're a little difference apart towards the end, say they don't overlap just perfectly and there's a little space in between. If it's within the tolerance of the work you do, the true center is in between those two arcs that are going to look like parentheses. So just eyeball the middle and put a center punch in there and hit it, and you can call that good. Or you can readjust your Trammel points one more time and give it a shot. So now we're going to talk about dividing the line into equal segments the hard way. So given line A to B, we want to divide it into 5 equal segments. So we build some line off point A at some angle. It really doesn't matter. It doesn't matter the length. It's usually nice to put it a little bit past point B, but that's all right. But open it up a little bit. And basically what we're going to do is we're going to build this line through point B parallel to it. But first we're going to mark, and it doesn't matter what the diameter is of these circles. They're not critical measurements. So you just want to open it up so you can, in this case, like draw 5 of them. I'm going to divide line AB into 5 segments. So you open it up and you draw a circle, and where it intersects a line, you draw another circle. And where the circle crosses a line, that's these arcs. And then you get to point C. And you don't really care what point C is. You'll see that in just a second. So you can just open your Trammel points up and do it. Then we're going to go to point C, and we're going to measure the distance to point B with the Trammel points. That's what this little sweep here is, just measuring the distance. Then we're going to go to point A, and we're going to draw a circle, basically just the bottom left quadrant of the arc, because we're building a parallelogram between A to C. So you'll notice if we have B being equal to C, then this new point is going to be below A. So that's why that arc's right there. Then we measure from point C to point A. So we need to know the length of this. And once we know the length of that, we move to point B, and we swing our arc. We're across the circle from point A, and we call that point D. I draw my line through point D and B, and I have a parallel line to number C. And then what you do is you put your Trammel points back up here in the original line and reset it from this A to the first arc. And you draw arcs on the line from D to B. In this case, I started in point B and worked to D. And then you draw straight lines from A to D and C to B, and where the arcs in between cross the parallel lines you drew, you draw a line through those arcs. And then where those angled parallel lines cross the horizontal A to B line, that distance is equal all the way across. In this case, I have it marked X. So it doesn't matter what angle you pick. It doesn't matter what A to C is. What you're doing is, marking off those lines equally and then using geometry to say, let's find what it is in the middle. And there's some mathematical theorem that says this all works. I don't know what that is, but it works. That's all you need to know. This is what you do if you don't have a tape measure. It is a little more complicated. I found the other way was a lot faster and more fruitful, even if I didn't know the exact starting number. So now you got your center lines down. I've taught you a bunch of techniques. So now we want to find a point off these center lines. I've named the horizontal one X and the vertical one Y and the intersection point C. So what I want to do is find a point off the center lines. It's 8 units off horizontal, so you go up the Y one 8, and off 6 units off vertical. So on the horizontal line X, you want to go 6 units off that. So this requires a tape measure, but you just set your Trammel points to 6 units and center the Trammel points at the center C and mark an arc on the horizontal center line X, and where it crosses that center line, that's point D. Okay. Then you set your Trammel points to 8 units, center it at point C, and on the Y-axis, you draw an arc where it crosses, and you call that point E, because that's 8 high, and now you're 6 wide, if you will. Then you take that same circle and you go down to point D, and you draw it again, and at the top you draw an arc, just like you did at the top when it's on C. Then you go back and set your Trammel points to the first radius you set around point C, and you put it on point E, and you draw that where the arc crosses the arc on the circle from point D, you mark that. That's point F, and that's how it works. You found your point. Now, after finding your point on that center line, you can draw new perpendicular lines off that point, and this is really easy because as part of finding that point, I also found 2 other squares of a corner. So I draw a line between E and F, which is parallel to line X, and that gives me the top. I draw a line from F through D, and that's parallel to the Y-axis there, and that gives me another side. So now I have my square. So now you can use the lines going through point F as new center lines, right? You got new center lines here. You can put a bolt circle on there, other shapes, a hatch opening or something. You can do quite a bit. You can combine all the Trammel point techniques that you've learned to these new center lines to create new points. This is how you use the fundamentals of Trammel points to lay out an entire project by building off the techniques together. And this is why you want to figure out ahead of time how you're going to do the layout work before you start. Because then you can plan your work and then execute your plan, and knowing where you're going next ensures you'll be accurate as you go all the way through. So now we're going to do dividing a circumference into equal segments, also known as bolt circles. Dividing circles into equal segments is a common activity used to set up center lines and angles to determine new lines. It's also used for bolt circles to attach different pieces of equipment together, pipe to pipe, pipe to equipment, equipment to equipment. It's also used when creating architecture and interior design, herringbone floors, for example. There are easy configurations to lay out, such as dividing circles into segments like a ruler, half, quarter, eighth, 16th, 32nd, etc. These simply rely on bisecting lines layout techniques. And there's more time-consuming ones to lay out, such as those divisions based on uneven numbers like 5, 7, 11, 13, or when they're not divided like a ruler. These are more reliant on the brute force method of selecting a distance, starting at the beginning, sequentially going around the circle. If the last arc doesn't cross the originating mark, adjust the Trammel points accordingly and try again until a complete circle of arcs crosses the starting point. Dividing circumference into equal segments, also known as both circles, page 2. So bolt holes can be laid on center or straddle center. This refers to whether the bolt holes are on the center lines or an equal distance apart from the center lines. So at first, straddling center lines appears confusing, but it's really quite simple to do. If there's 4 bolt holes straddling center, then simply double the number of bolts when going around the circle and use every other point straddling centers. So here you have 4 bolts on centers, and there's 1 bolt on each center line. For bolt holes, 4 bolt straddling centers, you find your center lines, you divide it into 8, and then you pick every other point. The points being between the center lines is where your bolt holes go. It's that easy. So, let's try it. Bolt holes on centers. Then we're going to divide that 90 degrees into 45s. And we're going to draw lines through those and put our bolts in there. Now we have 8. And then we're going to draw circles and arcs again between the existing holes where they're going to go. And we're bisecting them, so we're going to draw lines between them. We just keep doing that again, and now I have 16 bolts. And you can keep going and going and going, but usually after about 16 holes, you're better off using the method I'm describing next. So this is the brute force method. It works every time, although it's trial and error method of determining the bolt spacing, the cord length. So to determine the straight line distance between bolt holes typically requires trigonometry. However, you can estimate the cord length between bolt holes, make a set of passes, find the difference, adjust that, and then hopefully it fits the second time. So we're going to kind of follow this little procedure here. So first, the circumference of a circle is 2 pi r, or pi d, where r is the radius and d is the diameter, and pi is 3.145, blah, 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 to forever. So to estimate the circumference, multiply the diameter by 3. This is going to result in a circumference that's less than the actual circumference. Divide that estimated circumference by the number of bolt holes and use this as a starting dimension for the bolt hole cord length. It'll actually be small since you multiplied the circumference by 3 instead of pi, 3.145, but the cord length is less than the circumference divided by the number of bolt holes, since the circumference is curved and the cord is a straight line, so it all kind of works out for an initial estimate. So you set the Trammel points to this estimated cord length and starting at a center line, proceed sequentially draw arcs around the circle. Where the last arc should hit the original starting point, it'll come up a little short. Take this distance that come up short, divided by the number of bolt holes, and add it to the existing Trammel point distance. So if you had 10 holes and some distance, you take that distance divided by 10, take that tenth of whatever that distance was and add that to your Trammel point distance. So then you repeat the process of laying out bolt holes as described above, starting on the original mark. And again, if the last arc doesn't hit the starting point, divide this distance by the number of bolts, adjust the Trammel points, and repeat the process of laying out the bolt holes. And typically, you get it right after no more than 3 sweeps around the bolt circle. Sometimes you can tell how much the cord length is off when you get to the first quarter center line or the half center line. If so, take that distance between the last arc and the center line, divide by the number of arcs already laid out, adjust the Trammel points accordingly, and then repeat the process of laying out arcs from the initial starting point. You can get quite fast doing it this way with a little experience. It's not scary, it's just brute force way of determining the actual cord length. This is how you make money doing layout, not doing the academically correct mathematical or geographic, whatever way, but doing it the right way to save time and potential math errors. You can't argue with the correct chord spacing. Like anything, though, you always got to check your work. So I'll show you some tricks here. Okay, so now we're actually going to draw a bolt circle here. This is the brute force method for determining bolt circles, and it works every time, although it's a trial and error method to determining the bolt spacing or the chord length. So given this circle here, with a radius of 1, a diameter of 2, lay out 10 bolt holes on center. So you start by estimating the chord length. So this is 3. Instead of pi, we're just going to multiply by 3 times the diameter 2 is equal to 6. That's your estimated circumference. In this case, it's a little smaller than the actual circumference because we measured by 3 and not pi. But then you take that estimated circumference and you divide it by the number of bolt holes, in this case 10, to get 0.6, which is the spacing between the bolt holes, or the chord length. And you set the Trammel points to this length. Then starting at the origin up here at the top center line, you start sweeping your arcs. There's your first one, your second one, your third one. You go around the circle till you get to 10. And at the end of the 10th one, you'll notice it didn't cross the origin where you started. So that distance between your last arc and the origin is D. Now, I didn't draw the full circles on these sweeps this time because it gets kind of ugly looking because the circles start to overlap in the middle. And so just take my word for it. These are the sweeps. There's that distance D. And so you measure that. You divide that by the 10 bolt holes. And since you're a little short, you have to add that to the Trammel point length. So after you add that, you start at the origin again and you start drawing sweeps. Here's my first one, second, third, fourth, fifth, all the way around until I get to my 10th one. In this case, the 10th arc crossed the origin point, so everything's good. If it's a little long or a little short, you do the thing where you measure that distance, divide it by the number of bolt holes, make your adjustment to your Trammel points, and rerun your circles again. Usually 3 times does it. So in this case, it was right on the money. So you put your bolt holes where the arcs cross the circle, and it all fits. It's that easy. So you'll soon find you can use existing center lines to check the estimated chord length between bolt holes. In those instances where there's an even number of holes, at least 2 holes will fall on the starting center line. So if you started on the vertical center line at the bottom, halfway through on an even number of bolts, you'll have a bolt hole on the top center line. So if you find a large distance between that last arc and 100 degrees, you can measure that distance, divide it by half the number of holes, adjust the Trammel points accordingly. Then restart the origin, go around again. And this can save you some time because you don't have to complete the last half of that first circle. You made an adjustment already. If the number of bolt holes is a multiple of 4, a hole is going to fall on every center line, both vertical and horizontal. And you can check the chord length on all 4 center lines and adjust accordingly. So the first quarter, a half, 3/4, or all the way around. Once you finish the circuit around the circle and the last arc falls on the origin point, you can also do a double check by starting at the origin and going around the circle in the opposite direction. So if you started out clockwise, go around counterclockwise. This double checks every point. And sometimes you'll find a small difference starting to get bigger as you proceed around the circle. If you get to the end point and it's not excessive, then you can go back to each one of your points and simply use the middle between the 2 arcs at every point, as that's the true center. If you were to adjust your chord length to make it perfect, it's going to fall between the 2 arcs that you found by going both ways around that circle. And you can just visually put it in the middle and hit it with your hammer and it's done. So some typical tools needed for layout: tape measures and rulers, a machinist square, a 12-inch minimum, you have to have a 45-degree side too. And these allow you to move the blade length up and down. This is what you use to set the edge line, for an inch, inch and a half. And having that 45-degree angle side is good on small pieces. You can just flip it on there and draw your 45-degree line. You want a carpenter square, usually 2 feet by 3 feet. You can check your center lines that way a little faster. You don't actually have to measure a 3, 4, 5 triangle. Markers, a pencil, a scribe, a chalk, soapstone. Trammel points, straight edges, having a 2-foot one for small work, 4-foot, 8-foot, 12-foot, and 20-foot. Will get you anything. For steel, you need a hammer and a center punch, or any metal work really, even aluminum, copper. 1.5-inch spring clamps to clamp the tape measure. So if you have a piece of plate, you can clamp the tape measure to the plate on the edges so it doesn't move. And that way you can set your trammel point lengths, because then your tape's there solid and you can put your point down there and just move down the tape. Having magnets when you work with steel too, because then if you're in the middle of the plate and you have to do that, instead of using spring clamps, you can use the magnets, or you can use magnets for setting the edge of a straight edge. So when you go to the other end that's 12 feet away, you have a little resistance at the other end that allow you to get it lined up just right. A level, for those times you need a level. And then if you're doing steel work in a big fab shop, or you're marking it and it might get done the next day, you want to use a paint stick for marking dimensions, holes, piece marks, etc. Some circle trivia for you. Note you can draw a circle with a diameter D, a square with side lengths D, and a diamond with diagonals D, all from one center point, and they all fit inside the square. So here's 4 circles, kind of like a diamond, and you'll see how the circle, the square, and the diamond all fit in there, and they all have the same width distance involved. If you draw 4 circles as a square touching sides, you can do the same thing on these intersections here. It's actually the basis for a lot of artwork, in the Renaissance period in Europe, in the Mideast. A lot of Arabian architectures built off these kind of geometric patterns. This thing, if you draw, like 30 to 60 degree circles and all that, these little flowers, is known as the circle of life, or the flower of life. You see this a lot again in Asian and Middle Eastern art. And now, for those of you who are really wondering, well, what's the trigonometry part of figuring out chord lengths? Here's a little presentation. I won't go through it. You can read it, about how to find this chord length B to A deterministically using sines and cosines and all that. So I'll let this sit for a minute so you can read it, and then I'll go to the next page. Next page. So this is a little table. It's like a cheat sheet. Used to have something like this at work. So if you know the number of bolts, you can figure out the angle between the bolts. You can figure out the half angle between those bolts. You can find the sign of that by looking it up in tables or on your smartphone. And then you can figure out that this last right column is the chord length L with a radius 1 and a diameter 2. So here's the number of bolts, and if you just take 360 and divide it by the number of bolts, 2 gives 180. 360 divided by 3 is 120. 360 divided by 4 is 90 degrees. 6, 60 degrees, that's our hexagon. Octagon's 8, that's 45 degrees. So that's how you figure out the angles. And this can be handy if you want to use it. If not, like I say, you can figure it out with arcs and not have to worry about this stuff, because you can actually make mistakes this way. The other way, it's a little harder to make mistakes. Might be not as sophisticated, might take you a moment longer, but it's right because you're checking it as you go. It can't be, when you measure the chord, the trial and error way, the brute force way, the chord length's the chord length, and if it works, it works. That's it. That's a presentation. I hope you enjoyed it. And, if you want to get into fancier stuff, you can use Trammel points for building scrolls and everything else. Till then, see you later. Bye.